Hey, a little bit of magnetic forces today, thinking about how much attraction, repulsion, how much force these magnets put on each other. Now, of course, you know that if we have two permanent magnets, if you pull a couple things off the refrigerator, when you push them together, they will either attract, pull towards each other, or repel. That force comes from the magnetic fields interacting with each other. When you get two magnetic fields that interact, they will either repel or attract. There will be a force that's generated there. So we want to talk about those forces. I need to remind you about the right-hand rule here. You got two options. There's two ways to do this. If I have vector A and I do the cross product with vector B, if I multiply those two vectors, then we use this thing called the right-hand rule to get vector C, the resultant. All right? And the trick is that vector C will always be perpendicular to both A and to B. So there's only one way that that things can be. You can have three things that are all perpendicular to each other. You've got to have it in three dimensions. Okay, so if vector A points in the x direction, vector B points in the y direction, then vector C is going to point in the z direction. And there's this trick with the hand here that they're showing you. In the first way, the one on the left, what people say is to put your fingers in the direction of A. So imagine, just point the direction that your fingers would point for A. Curl them in the direction of B. So the guy's already rotated them towards the blue arrow there. And then his thumb points the direction of C. Remember how it has to be perpendicular? So you got A going forward, B to the left, and C is pointing upward at that point. The way on the right is another common way to do this. You can make this little three-fingered handgun there that you see, and you can point your index finger in the direction of the first vector, vector A. You can point your middle finger in the direction of vector B, and then vector C will be vertical again. Okay, so either way works. We need those to do cross products to see which direction these forces are. Everything's in three dimensions. That's hard to visualize. It's hard to draw a picture of, but we're going to do it anyway. Okay, I'll show you some tricks along the way. Now, here's the first one of these right-hand rules that we did some right-hand rules with the magnetic fields too. If you remember, we put our thumb in the direction of the current and our fingers pointed the direction of the magnetic field. That was a right-hand rule. And seems like there was something else, but I don't remember. Oh yeah, with the coil, right? You could either do it the way we just talked about, thumb in the direction of the current, fingers point the direction of the magnetic field, or you could put your fingers in the direction of the current over the top of the loop and back down, and then your thumb would point the direction of the magnetic field. That's a right-hand rule, and it works because of the cross product, the multiplication of two vectors. So here's another right-hand rule. When I have a charged particle that is moving in a magnetic field, it will have a force on it. Okay? We know that moving charges generate magnetic fields. So right here, I'm showing this represents a charged particle. It's got some charge plus Q, and it's moving to the right along vector V. And those X's represent the magnetic field pointing into the board. And the red arrow, the F there, marks the direction of the force. So there's two parts of this. It's a vector. The force is a vector. So it's got a magnitude and it's got a direction. We treat them separately. All right. Over here is the formula. F equals QVB. And you can see how those are bold print. What they really mean by that is that those are both vectors. So you could come in here and say, I'm taking vector V and I'm doing the cross product. That's one of the ways to multiply vectors. Multiply it by vector B right there, and that's going to give me a vector F. Okay, you see that F has a direction. V has a direction, B has a direction. These X's again into the board. If you imagine arrow, oh, my board's twisted, that's what's going on. If you imagine an arrow like you might shoot with a bow, it's got a sharp pointy end over here, and then it's got the arrows, the fletchings, the feathers, whatever you want to call it, back here on the back. If I look at the front of the arrow, it looks like a dot coming at me. If I look at the back of the arrow, it's going to look like an X with the feathers going away from me. So anytime we draw this X here, that's the magnetic field, or whatever this represents, going into the board. We're looking at the back of the arrow right there. Sometimes they'll draw a little circle around the dot just to make sure that you don't think it's a fly that got squashed on the paper or something. All right, but when you do the cross product, you have to do this, V cross B, and the quick and dirty way to do it, especially if these are in polar notation, is to take the magnitude of the velocity and the magnitude of the magnetic field, and then you toss in a sine theta. If you're in 222, you've already seen that. If you're in 202, you don't need to worry about it. All right? But in this case, in the picture that I have drawn, the velocity is straight to the right, and the magnetic field is straight into the board, and that's a 90-degree angle. The motion here and the motion into the board is 90 degrees. I would come in here and say the sine of 90 degrees, and of course that's 1. Now if it were anything other than 90 degrees, then I'd have to put that angle there and take the sine of it and multiply Q times V times B times whatever that sine theta is. If it's perpendicular, the velocity is perpendicular to the magnetic field, and in that case, you don't have to worry about that sine part at all. Theta would be equal to 0. Theta would be equal to 90 degrees, and of course the sine of 90 degrees is 0. It's not 0, it's 1. Woo boy. There we go. Okay. So that's what we need to know there, and I'll try to draw a picture in just a little bit where it's not 90 degrees so that you can kind of see what's up with that. All right, but that's the thing. A problem might say something like the velocity is 4 meters per second, the magnetic field is 2 Tesla, and the charge is 1 Coulomb, and theta is 90 degrees. Okay? They might say it's moving perpendicular to the magnetic field, which would be the same thing, something. But all you have to do is you use the formula. And you'd come in here and say F equals QVB sine theta. And I look over here and say, oh, thank goodness, it's a 90-degree angle. So this part's going to just be a 1. I don't even have to worry about it. The charge was 1 Coulomb. V is 4 meters per second. And then B is 2 Tesla, like that. And I take 1 times 4 times 2 would be 8. And that comes out to newtons. If you remember our units for magnetic field, there was one where it was Newton amp per meter and all that. And that would work out here. If you want to see the gory details on that, which I guess, what did I just do? Here we go. What happens here is you've got coulombs right there. I'm going to take that second and scoot it up underneath the coulomb there. So now I've got a coulomb per second, which would be this part right here and this part right there. And then I've got a meter and a Tesla. Okay. The other unit for instead of Tesla, here's my coulomb per second, there's the meter. Instead of Tesla, I'm going to write Newton amp over meter. And you can see that the meter cancels right there. A coulomb per second is an amp. I think the amp's actually on the bottom, isn't it? Newton per amp meter. Yeah. Okay. And so here's an amp, and I got a Newton per amp, and the amp cancels, and there's the Newton right there. All right. This should, it's a force. It should come out in newtons. It does. Sorry about tangling that up. Okay. But that's all you got to do. All right. 9 times out of 10, you're just doing this right here. If there is an angle, then you put it in there, and it's fine. Let me show you these. These are all perpendicular, so we don't have to worry about the angle just yet. But let me do this, and what I'd like you to do is to reach in your pocket and get your right hand out and do this with me, all right? Because this does take some practice. It is kind of weird. There are a bunch of these, 6 of these here. Let's kind of walk through them. For this first one, remember what I'm trying to do. My force equals Q V cross B. Now the order is important here. This is one of the few things in mathematics where you can't switch the order. If you switch B and V, then you get a vector in the opposite direction. This is non-commutative. You cannot switch the order in this, so be careful with it. Keep it in order. You got V first, so you want to start off with your fingers in the direction of V. So I am pointing my fingers in the direction of that green arrow right there. Then I need to go to the second vector, which is B. Q is not a vector, it's just a constant, just a scalar number. So I'm not worried about that. I'm just thinking about the 2 vectors. V is a vector and it goes down. B comes out of the board. There's some of those arrowheads, arrow points coming at us right there. Here's some arrows going away from us right there, all right? And so what I need to do is to point my fingers in the direction of the red arrow, and then since B is coming at me, I need to curl my fingers toward me. My hand needs to go down the screen and then curl towards me. That means that my thumb has to point to the left. That's what we wanted to know. The direction of your thumb at that point is the direction of the force. So I'm going to come in here and draw the force this way. All right. If I had a charged particle right here that were moving in the direction of V, it would experience a force to the left, and it would take a path something like that. The force would divert it, bend it away from the green line, and it's going to go that way. All right, let's do the second one here. This time the velocity is up. That's first. So I point my fingers up the screen. I need to curl my fingers in the direction of B, to the right. So I need to roll my hand and curl my fingers to the right. That forces my thumb into the board. So the force right here would be into the board, like that. All right. V, point up the screen. Then you got to roll your hand over. Try not to tear your wrist or anything there. Curl your fingers to the right, and your thumb is pointing into or towards the screen right there. So that would be the direction of the second one. Number 3, got my fingers pointed to the right along the green arrow. The magnetic field is going into the board. I'm looking at the back of the arrow there, so I'm curling my fingers into the board, and my thumb points up. Like that. This is a kind of weird one right here. Let's hold off on that one. Right here, I've got the velocity into the board. So I'm pointing my fingers toward the screen. I've got to roll my hand, palm up, and curl my fingers up. That makes my thumb point to the right. Like that. Okay? This last one right here, I got the velocity coming out at me. So kind of figure out what you got to do to get your fingers pointing at you. And then you got to roll your hand over and curl your fingers to the left. That points my thumb downward. So the force would be downward here. I hope that makes sense. I could get on Zoom sometime and turn the camera on and do some of these if you want. Now let's go back to D real quick here. this one's kind of weird. Let's write out the formula. F equals QVB sine theta. And the angle right here between V and B, V is to the left, B is to the right. There's an angle difference there of 180 degrees. Okay? So if I come down here and I put sine of 180, sine of 180 is 0. So the force Q times V times B times 0 is 0. This one experiences no force, and it would just keep moving along the straight green line right there and not be diverted at all. The same thing would happen if the velocity were parallel to the magnetic field. Theta equals 0. I'd put a 0 here, that'd be a 0, 0. Okay? So anytime the velocity is in the same direction as B, I don't get any force on it at all. All right? Now, I wanted to do one where the angle was not 90 degrees. All of these were 90 degrees except for this weird one here. Let's say that my magnetic field points that way. And let's say that my velocity well, no, it still wouldn't want to put it. Let me draw it. I might have should have thought about this a little more. There's that. And yeah, okay, we can do it this way. And right there is my velocity. Right, these are the lines of magnetic, the field. Okay? So what I need to do is V is going this way, and I'm looking at that angle right here, theta, and see how that's not a 90 degree. 90 degree would be straight across them like this. Okay? This one's not a 90 degree. It's over here, 70 degrees or something. Okay? So the only thing different that I'd have to do, it's not a big deal, but you just have QVB sine 70 if that's what they tell you in the problem. And when you multiply by the sine of 70, it's going to knock the value down just a little bit. So right here, sine 70 degrees, you know, is 0.93. So it'd be 94% of what it would be if it were perpendicular. Yeah. Here's 100%. And as you come down this way, this one we said was 0%, right? As you go more and more parallel to it, you're going to get less and less force. Which way would that force be? Well, if it's moving up, and I have to curl my fingers to the right, that would be into the board. Same thing here. This one's going along this line, and then I need to curl my fingers in the direction of V. So it's still into the board, but the magnitude is less than if it were straight across, if it were perpendicular to it. All right? Don't worry too much about that. But if you see an angle, just toss in sine theta. It'll be fine. All right? Here's one right here. Okay. Electron moving at 4 times 10 to the third meters per second. That's just 4,000. Let's just put in a 4,000 there. You want to? Okay, meters per second. In a magnetic field experiences magnetic force of 1.4 times 10 to the negative 16. What angle does it make? I don't know what this is right here, but that's not the right number, is it? Looks like we got, well, we do have the, there's the velocity V. Here's the magnetic field B. I'm looking at those units, meters per second, Tesla. Tell me what these are. I've got the force, and it's in newtons, which makes sense. So let me put that down here. I don't know why it says force equals 0 up there. Let's just scribble that out. And little bitty force here, 1.4 times 10 to the negative 16 newtons. Okay, now remember that that's a little bitty force, but we're talking about on an electron, which has a very, very, very small mass. So we'll still get a pretty pronounced effect on this thing here. What angle does the velocity of the electron make with the magnetic field? All right. So over here's our formula. F equals QVB sine theta. We want to find theta. So we came in and divided both sides by QVB. Canceled all that. Ended up with this right here. I want to get rid of sine. Anytime I'm looking for the angle, it's an arc sine, arc cosine, arc tangent, something, right? So I've got that. And now I need to say, here's the arc sine of the force, little bitty number, 1.4 times 10 to the negative 16 newtons. I'm dividing by the charge, which is, this is an electron. Okay? So we use what we know about electrons. We talked about that in the electricity stuff. The charge of an electron is 1.6 times 10 to the negative 19 coulombs. So sometimes they want you to know that number. I'll put it right there. I need the velocity, and that was 4,000 meters per second. And the magnetic field B is 1.25 Tesla. And I want to see what that comes up to. So right here, I have second sine, and then I need to do 1.4 E negative 6. It's not 6, that's a 16, isn't it? Okay, let me go back and get a 16 in there. I'll write it in just a second. Divided by 1.6 E negative 19. Also divided by 4,000 instead of 400. And also divided by 1.25 Tesla. All right, so that says 16 degrees right there. I already forgot what the decimal was. 16.3, something like that. Okay, and again, this should have been 4,000. That should be negative 16. And there you kind of sort of go. Okay. So that's the angle that it makes right here with the between the velocity and the magnetic field. All right. If that were to go all the way to 90, that'd be the maximum force. If it went down to 0, the force would be 0. So, that's what that force 0 is. Okay, that goes with this right here. That makes sense. I did this a long time ago, so just re-recording it here for sound quality. All right, check this out. We've already said that a charged particle moving in a magnetic field is going to experience a force. So let's take this charged particle at several different places. I want to start with it down here. When I have this charge right here, the velocity is shown as this way. The magnetic field is into the board. So I have to point my fingers to the right, curl them into the board, and the force vector points up. Right there, that red arrow. Point your fingers this way, curl them into the board, thumb points up. So it gets a force upwards, right? That's going to change its path, and it's going to come like this. All right? Let's do it again. When the particle is right here, it is now moving that way, so I need to point my fingers upwards, curl them into the board, and now my thumb points to the left. So I draw the force in there. I could have done any point here in the middle as well. When it's right here, the velocity is this way. I point my fingers that way, curl into the board, and I would get the force going like that. Okay? That diverts its path, comes on around here. At this moment, my velocity is to the left, so I point my fingers to the left. I curl my fingers into the board and my thumb points down. All of these point right there at the center of this arc that it's making. This is now a centripetal force. And if you remember from Physics 1, we talked about circular motion and how anytime you see something moving in a circle, you've got to have a centripetal force. That centripetal force, F sub c, is equal to mv squared over r. So what we've done is we've taken the QVB sine theta right there, and then we've set it equal to the centripetal force. The magnetic force, the force due to the magnetic field, is equal to the centripetal force that causes this thing to move in a circle. And what we've done here is to solve this thing for r, because they want to know what is the radius of the circular path. We're looking for the distance between the center of the circle and the electron here. Right there. Okay, so the algebra is already done. We're just trying to solve for r. In this case, we can ignore sine theta because the velocity is here and the magnetic field is perpendicular to that. So I'm just scratching off sine theta, letting that be a 1, not worrying about it. I'm down to this right here. At this point, we do a swappy thing. We could multiply both sides by r, cancel there, and simultaneously divide both sides by QVB. That would cancel all that, leaving me just r on the left. And I'd have mv squared over QVB on the right there. And we could put those numbers in and see what we get. The mass of this thing is right here on the thing. Okay, so that hopefully would be given. You might know the mass of an electron if you've been working in your chemistry class. And my calculator's hung up, so I'm going to turn that off and see if I can get it back here. Let's try one more thing. Alright, that should do it. And so I've got 9.1 times 10 to the negative 31 times v squared. That thing was moving 7.5 million meters per second. 7.5 E6. You know that the speed of light is 3 times 10 to the 8 meters per second. So this thing's moving pretty fast. Not quite as fast as it can, but it's moving pretty fast. I need to also divide by the charge. It's an electron, so this is 1.6 E negative 19. And then the, there's another velocity. You can actually cancel that velocity with one of those right there, but I didn't, so I'm going to go ahead and put it in one more time. Be 7.5 E6, and then divide by the magnetic field, which was 1 times 10 to the negative 5th. That's pretty weak magnetic field. E negative 5. All right, and if I did everything right, that would be 4.26, 4.3 meters would be the radius of that circle that the thing moves in. Now, remember, this is it's pretty fast, right? And but that's kind of an interesting problem. I don't know how much you know about particle accelerators, and I don't have a browser up right now, but when you look at particle accelerators, they're usually, not always, but they're usually circular. So let me see if I can't find a picture or two here for you. Here's one from above, and you see the big circular path right there. So they're accelerating those things around faster and faster. They've got another one going over here. Then they smash the two together and see what flies out. Okay. Here's down inside the tunnel, and you've got these tubes that have lots of magnets. They're accelerating them, and they kind of naturally move in that circle. But they have big sensors. This is on at CERN in Switzerland. They've got the big toy right now because Congress decided we didn't really need one after all. Shut down the super collider in Texas, and you know, these are pretty amazing machines here, and but they usually have that circular pattern like that. So go build you one of those if you like. You need some magnets. You need some charged particles. You'll be fine. All right. Now there's one other detail here I really should have put in, and I didn't. So we kind of glossed over this, but let me say a word about it here. Notice that this is an electron, and with an electron you really should have a negative charge right there. Okay? So an electron is actually going to curve the opposite direction. When you put a negative right there, you're going to get a negative answer, and of course a negative answer in physics means opposite direction. So it would have been better to say, here's my magnetic field, and I've got that charged particle moving this way, and it's going to go in a path that way. Electrons would actually go this way, and protons, positive charges, would go that way. When you look at some of the old cloud chamber photographs, this is actually how they discovered, well, we always, not always, but you know, way back ancient Egypt days, we knew about positive and negative charges, but I can't get a decent picture here, but I don't even know what, oh, Pinterest. I hate Pinterest. What a bunch of mess. Alright, let's go back here somewhere. All of these crazy pictures here are the pathways of charged particles through a fog. You take some dry ice and liquid hydrogen, something, and you super chill the air. So when a particle zips through it, it leaves a condensation trail, just like a jet trail would. Okay. Some of these paths curve to the left, and some of them, like this one right here, curves to the right. Okay. And so the point is that you can tell which ones are positive and which ones are negative. It's about back in the 30s when they were doing this kind of for the first time, and they knew about positive charges and negative charges, and so they took this picture or something like it and said, oh yeah, there's the positive charges spinning this way and the negative charges this way. And somebody said, well, what's all the lines going straight through there? And I said, gee, I don't know, positive ought to go one way and negative the other way. What's left? And that's literally how they discovered the neutron, that here was a particle that was neutral, that had no charge. And since the Q is 0, then the force is going to be 0, right? If I put a 0 right there, then the whole thing's 0, and it's just going to stream on through in a straight path. So kind of try to remember to do that. If it's a negative charge, I guess you could use your left hand and it would come out right, but really probably better to go ahead and use your right hand, and then whichever way your thumb says, remember that, oh, it's a negative charge. I got to do it the other way. All right. That's kind of confusing, but it works out and you get used to it. What if I had a whole bunch of charges moving together? What if I had a current that was moving in a pre-existing magnetic field? Now, in the last video, we saw that currents generate their own magnetic field. So now I've got a magnetic field in a magnetic field, and those two magnetic fields are either going to push or pull on each other, attract or repel. So anytime we have a current moving in a magnetic field, a wire, then it's going to experience a force on it. There's another right-hand rule right here. It's easy to remember because the I is first and the B is second. Those are the vectors. I has a direction, B has a direction. I don't really know how L, the length of the wire, came to be in the middle. To me, it would make more sense to write L I cross B like that. But for some reason, the L always shows up in the middle. But whatever. We can put it there. Just remember that the L, the length, doesn't have a direction, and so we're thinking about the direction of the current and the direction of the magnetic field. It's a right-hand rule. I is first, so I'm going to put my fingers to the right. When it says that I points to the right, that's the first vector. You point your fingers to the right. B is the second vector. It's into the board, so I've got my fingers moving to the right. I curl them into the board. That makes my thumb point upward, so the direction of the force is upward right there. If you had a problem, let's see if there's an example. Yeah, here's one. Find the current in a wire needed to levitate it. What if we wanted to overcome gravity and just have a wire float in midair? How much current would we have to use, or how much magnetic field would we have to have? In this case, they're asking us, we're going to change the current and make the thing just float. All right. Since there's a couple of forces, we drew a little force diagram here, and that's good practice anytime there's forces going on. Just go ahead and draw a little force diagram, free body diagram, and think about what's pushing and pulling on this wire to make it float. We've already said that if my current is going to the right in a magnetic field that's into the board, then my force due to the magnetic field is going to be up. So that's that one right there. Of course, gravity is trying to pull it down. So those are the two forces that I have. Here's Newton's second law. Sum of the forces equals mass times acceleration. I go to my picture and I say I got two arrows. And they say, well, what are they? And you write them down. One is up, so it's positive. One is down, so it's negative. And there is no acceleration. It's just levitating. It's floating. The acceleration equals 0. So we just put a 0 over there. Add mg to both sides. I know that the magnetic force is ILB. It's equal to mg. And I solve it for I right there. The mass of the wire is 10 grams, only we don't like grams. So I'm going to change that to kilograms. And then g is 9.8 meters per second squared. And the length of the wire is 50 centimeters. Only I don't like centimeters either, so that would be 0.5 meters. And the magnetic field is, what, half a Tesla. And then I come in here and, all right, right there. I come in here and I can punch that up, see what I get. Here's 0.010, if you like, times 9.8, divided by 0.5, also divided by 0.5, and that comes up to 0.392. Okay, that's not a very heavy wire, but and it is a pretty strong magnetic field, right? Half a Tesla, so that's pretty hefty field. But 0.392 amps would do the trick there, and that wire would just hover in the air, just float there. Okay, so that's kind of neat. What if I have two wires? Let's say that the current in this one goes to the right. That would mean that I could draw the magnetic field. Point your thumb to the right, and then curl your fingers around the wire. It's going to come up out of the board over here. And it's going to go over the top of the wire and back down into the board on this side. All right. And you can have lots of fun drawing all those if you want. I'm going to stop right there. The important part is that it goes into the board here and out right there. Okay. The second wire has a current. The second wire has a current. It's either to the right or to the left, so let's just arbitrarily say that it's also to the right. And that means that I need to point my thumb to the right. My fingers come out of the board over here, so my magnetic field is coming up on this side. And again, it's going to cross over and back down into the board on that side. Okay. I guess the point that we're most interested in is right here. I have two magnetic fields, and those two magnetic fields are going to interact with each other. They will either push or pull, and right here it tells us if they are in opposite directions, the force is repulsive. Ours were in the same direction. Current was to the right, current was to the right. Same direction, the force is attractive. So that's what we've got here. These two wires will experience a little pull towards each other like that. I like to remember that a lamp cord is repulsive. Okay, if you plug in a lamp, right, here's a poorly drawn lamp, okay, but the cord goes over here. There are two wires that go to the wall, and you plug that thing in. The current's going this way in one of them and this way in the other. Those are opposite directions, and those are repulsive. A lamp cord is trying to push those two wires apart. Okay, now it turns out it's a really, really small force, so it's never going to overcome the, not in, household kind of currents, not going to overcome the strength of the plastic insulation that's holding it all together. But if you had big currents, then something could happen here. Let's see if I got an example. Yeah, here's one. Two 6-meter long straight parallel wires are 10 centimeters apart. One carries a current of 2 amps, the other 5 amps. What is the force? So this is a force per length formula right there. How much force per length? So what I've done is multiply both sides by L, and it's come up over here on the right. And I need to do mu I1 I2 L and divide by 2 pi S R S whatever. It's that distance between the two wires right there. Okay. We used the mu with the pi just so that it would cancel the pi on the bottom. That's up to you, I guess. But here's the number that we get. Whole bunch of units, Tesla meter per amp right there. I got an amp and a meter, and here's a meter, and a whole bunch of stuff cancels. This amp is going to cancel one of them. There's an amp, and here's a meter on the bottom. There's a meter on the top, and all kind of stuff goes on there. Right there, a Tesla is a Newton per amp meter, and so the meter cancels the meter, and the amp cancels the amp, and there's a Newton right there. So we're down to the right thing. Little bitty force, okay? Like I was saying, a lamp cord's never going to blow itself apart right there. But if you had big currents, then maybe you need to think about it. Or if you're on a very small scale, there's a thing called the Hall effect, and it kind of works like this, where magnetic fields will push charges to one side or the other, and so in some cases this is something really worth worrying about. On everyday things, we're talking about 0.00012 newtons. All right, not a big deal. All right, but that's another thing there, another where magnetic fields cause a force. This, though, this is a pretty important one. I've got a magnet here. It's typically a permanent magnet, but an electromagnet will also work, either one. And when I pass a current through a loop right here, that's going to create a magnetic field. And that magnetic field will interact with this magnetic field and put a force on it. And specifically here, this thing is made to rotate. It spins, and so that wire way over here, some distance r away from the axis of rotation, and a force on that wire way over there means that I have a torque. And so this is how much torque an electric motor generates, because that's what we're talking about here. This is an electric motor, and that's all you have to do. You make a loop of wire, run electricity through it, make sure it's in a magnetic field to begin with, and your current here will generate its magnetic field, which will push on that magnetic field and spin your motor. All right. There's some parts here that you could talk about. I guess the brush is a little thing that comes up here and touches on this little conductor commutator, it's called, to carry the electricity even as this thing twists. I mean, if you just hooked a wire on it, the wire would twist up and break in, a quarter of a second or something. So there's a little thing that just touches there and passes that electricity. Those are usually made out of carbon. And sometimes if you have some real old tools or something that your parents or grandparents or something, the carbon brushes are worn out. You can buy new carbon brushes and undo a screw and put it in there. It's on a little spring to hold it up tight to the commutator and stuff, and make Grandpa's old drill work again. It's kind of neat. But it's kind of like graphite. It's carbon and something like that. Check it out right here. See the little dot right there? That means that the current is coming out of the board. The magnetic field is to the right. So if you put your fingers out of the board and curl them right, you get an upward force like is shown. Meanwhile, on the other side, the current is into the board. So I've got my fingers pointing at the screen, and then I roll my hand over to where I can curl my fingers to the right. That puts a downward force. So it's pushing up on this side, down on that side. That means it's going to spin this way. All right. A little bit later on, it's here. You could do the whole thing again. Fingers out, curl to the right, upward force. This one's going to be a downward force. It keeps rotating right there. You get a little bit of trouble right here because now when I put my fingers out of the board and curl to the right, I get an upward force, and this thing can't rotate upward. It can't move up anymore. It's already moved from here all the way up to there. It's at the top. So it needs to start going back down right there. So your motor needs to have enough mass, or it needs to have a flywheel, enough momentum to keep going past that point right there. If you don't have enough mass, you can make a little paperclip motor. Look up YouTube, paperclip motor. You can make one, for 2 cents or something. Battery and a paperclip and a couple paperclips, I guess, for a little stand. And if it doesn't have enough mass, then it's going to get hung up right there and just kind of vibrate and hum and get hot. A little thing like this, right? Just a real simple little coil. The battery is passing electricity through it. You got a little magnet down here that's putting magnetic field lines through there, and that thing will sit there bzzz, and just spin like it. That's all a motor is. Okay. Now this one only has one winding, so another trick that you can do instead of having enough mass to get it through there is to have multiple windings. That let's see if we can get a picture. See how usually there's a whole bunch of different windings, and that way it's not just one winding. Once you get that one there, then you can the others will carry it on through. And but on that simple paperclip thing, you kind of have to give it a spin to get it started so that it's got enough momentum to get past that point right there. All right. Anyway, that makes a torque. Remember, torque causes rotation. I'm putting a force at a distance. So there's my torque. The distance would be the width of this coil right there divided by 2. I need to go from the axis of rotation to where the force is applied. And then, of course, the force is ILB sine theta. And so that's that part, if you need that right there. All right. So that's all about magnetic force, how forces act on, the forces that are generated between currents, between moving charges, all of that. You need all those on your card. And, there's really only a couple cases. You got the moving charge in a magnetic field. You got the force on a wire, on a current. You got the force between two currents. You got the torque on a loop in a magnetic field in order to make a motor. Okay, so it's really only 4 or 5 things there. Jot those down on your card, do the problems, and see if that doesn't make sense. If not, you know where to get in touch with me, so please do. Thank you very much. Have a good day.